recording on this computer. Here we go. Perfect. Okay. So the E2 reaction mechanism is an elimination mechanism that is very similar to SN2, okay? And it's very similar in two ways. One is everything happens very, very fast. That's the reason why we don't even have a transition state. We don't even have an intermediate for these reactions. Instead, we have what is called a transition state. We go from this initial form in which you have a leaving group over here. A base comes in, takes away a hydrogen, builds a double bond, kicks out your leaving group. And all of those things happen very rapidly, one after the other, okay? So E2 means that we're gonna do an elimination, and that elimination is gonna be bimolecular, which means we're going to take away this hydrogen and get rid of the leaving group within the same transition state. I know that doesn't mean a lot to you yet, but we will get to that. Okay, so when you do an elimination reaction, you can get different kinds of products. And that's the reason why we have this handy rule here that's called Zaitsev's rule. Now, I don't know if you noticed this when you were watching the video for this reaction, but Zaitsev's rule, Zaitsev is a guy that used to work with Markovnikov. You guys remember Markovnikov's rule? What did Markovnikov's rule say in chapter 4? If you're gonna add a hydrogen, where do you add that hydrogen?
You add it where there's the most hydrogens?
You add it to the side where there's the most hydrogen. That's true, Kara. So Zaitsev's rule is the opposite. Zaitsev's rule says, if you're gonna take away a hydrogen, you're gonna take it away from the side that has the least number of hydrogens, okay? So let me show you how we would apply Zaitsev's rule in a case like this. So here is the compound that we're going to do our elimination on, okay? Everybody can see my cursor here? I'm right under 2-bromobutane. You see the little arrow moving here?
I don't know why, but I can't see your cursor.
You can't see my cursor?
No.
Okay, let's try this. Can you see it now?
Yeah.
Okay, good. So this is the compound that we want to do an elimination reaction in, okay? The first thing, the first job that you have is you need to figure out where is the leaving group, because we're going to eliminate and build a double bond that has to be touching the carbon that has the leaving group. You with me here? Okay, so the leaving group is this bromine that's right here in pink. Do you see it?
Yes.
So if we're going to do an elimination reaction, it has to go, and doing an elimination reaction, we're gonna build a double bond. The double bond has to touch this carbon because this carbon is the one that has the leaving group. You guys understand that much? We good here?
Yes.
Okay. So where are the carbons that are right next to the carbon that has the leaving group? We have one over here, right? We're gonna call carbon 1. Can everybody see carbon 1? And we're gonna have another one over here, which we're gonna call carbon 3, okay? 1, 2, 3. You guys with me? So there's two choices when we make our double bond. We're going to eliminate this bromine, and we're gonna create a double bond, and the double bond can go either here between carbons 1 and 2, or here between carbons 2 and 3, okay? And that's what the product is showing you. If we make the double bond between carbons 2 and 3, your double bond would end up right here in the middle. See that? And if we make the double bond between carbons 1 and 2, which is right here, your double bond would end up here. And that would be this product that you see on this side, okay? Now the question is, which one of those double bonds is gonna be more likely? I'm giving you the amounts that we found when we actually did this reaction, but there's a way for you to predict which one of these guys is gonna be the major product, okay? And the way to predict that is to see where is the leaving group. The leaving group is right here. Where are the neighboring carbons? The neighboring carbons are carbon 1 and carbon 3. And I want you to tell me between carbon 1 and carbon 3, which one of them has the least number of hydrogens directly attached to it?
3.
Carbon 3, right? Carbon number 1 has 3 hydrogens directly attached to it. Carbon number 3 has 2 hydrogens directly attached to it. Say-Sep's rule, which is the opposite of Marconico's rule, says if you're going to take away a hydrogen to make a double bond, you take it from the carbon that has the least number of hydrogens. So you would take it from here. Are we following along? Okay, I think if we drew this on our whiteboard, that might be helpful to everybody. So let's try that. So let's remember that we're going to do the reaction of 2-bromobutane with a strong base. So I'm going to stop sharing the overheads here. And let me share my whiteboard so we can do that reaction together. Okay, here we go. Now you'll need to be patient with me because my drawing skills on the whiteboard are not there yet, okay? But if we are gonna do bromobutane, we have 1, 2, 3, and 4 carbons, you see that? And on carbon number 2, we have a bromine attached to it, okay? So let me put a bromine right here. At least the bromine looks good. The rest doesn't look so good. Okay, and we're gonna use a strong base. And in the example that was in the overheads, the strong base was sodium ethoxide, I believe, which is CH3CH2O minus. Is it clear to you guys that this is a strong base, but it doesn't matter very much what base we use as long as we use a strong base?
Yeah.
Yeah? Okay. So this is going to be your strong base. Let me put here in parentheses. This is a strong base. Okay. So what is the base going to do? The base is going to attack one of the hydrogens that are neighboring the carbon that has the leaving group. Okay. So first of all, where is the carbon that has the leaving group? This is the carbon that has the leaving group, right? So what are the carbons that we have to consider to make that double bond with? They have to be directly neighboring this carbon. So you can make a double bond with this guy, which is carbon 1, or you can make a double bond with this guy, which is carbon 3. Are we agreed on that? Yeah? Okay. So let me erase these things here so we can go a little bit cleaner. So let's consider how many hydrogens are attached to carbon 1. Let's draw them here. Carbon 1 is at the very end, right? So how many hydrogens are attached to it? Some words would be nice, guys. I'm all alone here.
3.
3.
Right? Can we see it? 3 hydrogens there? On this carbon and this side, we only have room to add 2 hydrogens, right? Because that carbon continues on. Oops, that doesn't look like a hydrogen. I hate that my drawing skills are so rudimentary. I hope you will forgive me. There we go. Okay, are we all on board that this is the situation that we're facing? Yeah? And now we're going to take our base, our strong base, and the base is going to come and it's going to take away a hydrogen. It can take away a hydrogen from this side, or it can take away a hydrogen from this side. Say-Sep's rule allows you to predict which one of those sides is going to be more attractive for that base. Okay? So where do you think the base is going to want to come? To this side, which has 3 hydrogens, or to this side, which has 2 hydrogens? Say-Sep's rule says take away a hydrogen from the side that has the least amount of hydrogen. So where should I go? To carbon 1 or to carbon 3?
Carbon 3.
I should go to carbon 3. So here's my base, okay? I'm going to take my base and I'm going to come and I'm going to steal this hydrogen right here. Any of the hydrogens will work. I'm just going to take that one because it's handy, okay? In the same motion, I'm going to take this electron pair and I'm going to build my double bond right here. And in the same motion, I'm going to kick this bromine out of here. Y'all with me? So let's draw the product of that reaction. Let me draw an arrow because I learned how to do arrows and now I'm unbearable. There's my arrow, okay? So let's draw the product of that reaction. The product of the reaction, the carbon skeleton should be the same that we had before, okay? So 1, 2, 3, and 4 carbons. And where should I put the double bond that I made? Should it go right here in the middle?
Yeah.
Between carbons 1 and 2? Yes.
Yes.
And according to Marconikov's rule, this is what we would call the major product of that reaction. Major because we get the most of it, okay? Now, there's another product of that reaction, and that other product is what we would call the minor product. So let's see what the minor product would look like. The minor product is the one that gets formed on the other side. So I'm gonna take a different color, because I can, and I have lots of colors. So I'm gonna do the other one in blue, okay? I'm gonna take the same base, the same strong base, but instead of taking the hydrogen from carbon 3, I'm gonna take a hydrogen from carbon 1. You're with me here? I take this hydrogen, I use this electron pair to build a double bond right there, and I kick the bromine out. Is this color scheme working for you guys? Can we see that two things are going on? So if I'm gonna do the minor product, I'm still gonna draw the 4 carbons in a row, right? Now my double bond happened here between carbons 1 and 2. So there's my double bond, okay? Wow, that was a very straight double bond. I hope you appreciate that. And what else is gonna be around this solution after I did this? Well, there's definitely gonna be some bromine left over, right? Bromine with a negative charge, which came from here. And there's also going to be some of your base, CH3, CH2, OH. And the base comes, I don't know where the D came from. There we go. The base combined with these hydrogens to give you this alcohol that you find on this side, okay? Now, just so we're clear, the stuff that is on this side of the arrow, I am not really worried about, okay? All of that stuff is not important to me. What's important to me is that you can give me the major organic product and the minor organic product, because that's what I'm gonna be asking you about on the test, okay? So those are the things that I'm really worried about. This other stuff, I'm only putting it there because I feel like you guys might want to know what else happened. But the important thing is that we have a major organic product and a minor organic product. How did we figure out who was the major and the minor? We use Say-Sev's rule. Are we getting on board with these things? Does that make sense to everybody?
Yes.
Yes, it definitely make more sense.
More or less? Okay. So maybe we should go back to the overheads, or maybe we should do a different example here before we move on. So let's do, but you guys are gonna have to help me, okay? I refuse to do this all by myself. 2-bromo, 2-methyl butane. Okay, let me show you another example that's from the overheads, but I think it might have gone a little bit over your head in the previous, in the video that you saw. Okay, is it okay if I erase what's on the whiteboard so we can do something new? Remember, we're recording, so you can always go back, okay? So now we're gonna do another E2 reaction, and the E2 reaction that we're gonna do is coming from the overheads, and is the one of 2-bromo, 2-methyl butane with a strong base. So 2-bromo, 2-methyl butane. So I'm gonna put my bromine there to make it look good. So let's make sure that I've drawn the correct thing. 1, 2, 3, and 4 carbons, so it's butane. On carbon 2, we have a bromine and we have a methyl group. Everybody with me? Yeah?
Yes.
And we're gonna do an elimination reaction. So we're gonna use one of the strong bases that you can use for elimination, okay? And I think in the overheads, the strong base that was used in this case was still sodium ethoxide. So we're gonna go for the same one. CH3, CH2O minus is your base. And this is a strong base. And the reason why I'm writing strong base here is because I don't want you to get all confused by what this big guy does here. What this big guy does is it takes away a proton, which is what bases always do, okay? This is what a strong base is for. Okay, so let's think about this example. We know where the leaving group is located, right? The leaving group is attached to this carbon here. So any double bond that we make has to be touching this carbon right here. Can we all see that? Okay. And the next question for you would be, how many hydrogens are in the two carbons that are directly attached to that one? In this case, how many carbons are directly attached to our interesting carbon?
3.
How many carbons do you see coming out of it?
3.
3.
3. 1, 2, and 3. Okay? Now, how many hydrogens are attached to this carbon up here?
3.
3, right? So that's going to be 3 hydrogens. Got that? And how many hydrogens would be attached to this carbon down here?
3.
Also 3, which I'm going to draw them just because I want to be thorough. And because I want to get better at drawing with my cursor, but I'm losing hope at this point. Okay, y'all see that? And then this is the last carbon that's attached to the one that has the leaving group. And there are 2 hydrogens attached to the carbon. Can we all see that?
Yeah.
Yes. So now let's apply, well, first of all, let me draw my arrow because that's going to impress all of you. There you go, perfect arrow. And now you guys need to tell me, of the 3 carbons that are adjacent to this guy, hold on, I need to fix this hydrogen because it looks so bad. It's just killing me. Let me fix that. Of the 3 carbons that are adjacent to this one, I'm going to name those guys carbon A, carbon B, and carbon C totally randomly, just so we can talk about them. Which one of those looks like the best place to take away a hydrogen from? A, B, or C?
A.
A, because according to Saysev's rule, if we are going to take away a hydrogen, we take it away from the side with the least hydrogen, right? I'm going to take away hydrogen from carbon A. There you go. I'm going to take this
I
hydrogen.
don't think I can't hear you.
Did I miss somebody?
That's just me or not.
Yeah.
You got really quiet.
We can't hear you.
You can't hear me?
It's really, really, really faint.
Yeah.
Okay, I'm not sure why. How about now? Is that better?
Got you now.
That's better.
Okay, I just got a little closer. Okay, so your base comes and take away this hydrogen, right? Y'all can see that this hydrogen and this hydrogen would be the same thing. There's no difference between them, right? Take away the hydrogen, use the electron pair to build our double bond here, kick our bromine out. And if we do that, let's draw what our product would look like. And you would have 1, 2, 3, and 4 carbons. You still have that methyl group down here because nothing happened to it. And you have a double bond that goes right there. Can we see where that came from?
Yes.
And that's going to be what we call our major product because that's the one that was predicted by Dr. Zaitsev, right? That's the one that came from taking away hydrogen from the side with the least hydrogen. True?
Mm-hmm.
Okay. Now, there is another product that can be formed here. And that other product is going to come from taking away a hydrogen from the other side. So let's show what that product is going to look like. Would you guys like to take away a hydrogen from carbon B or carbon C?
They would yield the same thing, correct?
They would be the same thing. That's right. Carbon B and carbon C are equivalent to one another. They're both methyl groups. They're both coming out of the carbon that has the leaving group. So it doesn't matter if we pick B or C. Is that clear to everybody?
Yeah.
That they're equivalent? Would it be okay with everybody if I pick one out of carbon C?
Yeah.
Yeah? Would you let me do that? Okay. So let's pick a different color. And we're going to go from here. We're going to take away a hydrogen from carbon C, build a double bond right there, and then kick the bromine out. Okay? And if we do that, our second product is going to look like this. The 4 carbons in a row like they were before. There's a double bond right here. That's not bad. That's our double bond that we just made. And there's a methyl group at the end. Is that a major product or a minor product?
Minor.
Minor.
That one is a minor product. And as you know, there's also going to be other things in that reaction mixture, right? I'm going to put them down here. There's going to be some bromine with a negative charge, which came from here. And the base is going to combine with the hydrogen that it took away. And that will give you some ethanol as a result. Got that?
Yeah.
Yeah. The really important part is these two guys, the major product and the minor product, which are right here. Got it?
Mhm.
Okay.
Oh, Dr. Williams.
Yes.
Someone in the Zoom group chat put, I think it was Taylor Carmody. They put that the video had talked about the mono, di, and tri-substituted, and what exactly does that mean related to this, or is that even for elimination, for the elimination reaction?
Was that in the class website?
I believe so. I think it was in one of the it was in one of the YouTube videos for the chapter.
I haven't seen that comment. Taylor, was that you?
Yes, in the examples, I think it was for the E2 mechanism. When Nisha talked about if things are like mono, di, or tri substituted, and I was just confused on how to use that information.
I think that what Lanisha was trying to tell you is there's a different way to talk about Zaitsev's rule in which you look at how many substituents are around your double bond, okay? Whether you have 1 substituent or 2 or 3 around your double bond. I think that this way to look at Zaitsev's rule is simpler. So how about we just agree on using this way, and that way we don't have to worry about how many substituents we have.
Yeah, that's fair.
So just so you know, because I want you to be educated, not because it's going to be on the test. When you have a double bond that looks like this one right here, let me get my cursor so I can show you. When you have a double bond like this one right here, that's what we call, and that double bond would be considered to be not very substituted, because on one side of this double bond, you only have hydrogen, right? You don't have substituents down here. This double bond that we have here is what we would call more substituted, because it has more substituents around it. On this side, you have 2. On this side, you have 1. There's a way to formulate Zaitsev's rule that says you will make the double bond that has the most substituents, okay? That's what Lanisha was trying to explain to you. What I find from experience is that if we go with the simple version of Zaitsev's rule, and we consider it the opposite of Markovnikov's rule, most students get their questions right this way. So if you guys want to agree with me, we will go with this version of Zaitsev's rule. So if I give you an E2 question on the exam, and I ask you for the major product, what I want you to do is find the side that gives you the lower number of hydrogens and take your hydrogen away from there. Does that make sense?
Thank you, yes.
Does that make sense to you too, Kira?
Yeah, that makes sense.
Okay, so I'm gonna stop sharing the screen for a minute just to see if we have any questions in the chat that I haven't. There you go. Yeah, Do we have to know where to draw the arrows for the test? No, Drew, you don't have to know where to draw the arrows because I'm not gonna ask you for the mechanism, but I will ask you to show me the products. So Drew, if you're still around, I really need to make sure that, that you do know how to get to those products. And then Olivia has a question, do we need to know E1? No, you don't need to know E1 for the exam. I'm not putting the E1 reaction on the exam, only E2. Elimination in the presence of a strong base is the one that you need to know, okay? Olivia, I hope you got that.
I have
Okay,
a question.
so should we spend some time now talking about the exam review?
Dr. Williams,
What was that?
really quickly, do we also have to know like the anti for the like wedges and the dashes? I don't know. I think Lanisha described like anti substituents.
Yeah, what she was trying to tell you is when you're going to have a process that is either SN2 or E2, the attacking base or the incoming nucleophile has to come from the back. And a lot of people don't like to say backside attack because, you know, they have the mind of a 12-year-old like I do. So they like to call that an anti-attack because it's anti to the side where the living group is, okay? Now, if that is at all confusing, Zia, I suggest that you say backside attack, which has two advantages. It is funny and it's very descriptive, right? Because if something is coming from the back, it's coming opposite to the side that has the living group. Does that make sense?
Yes.
Yes. So instead of worrying about, you know, what the anti-attack means, we can all just agree that it's going to come from the back and then the living group has to leave out the other side. Make sense?
So that's why, oh, sorry.
Go ahead, Kara.
So that's why, like on one of the examples where it's asking you, like, hey, which product can be, like, which reaction can lead to the product? Let's say, for example, like the anti, if you have like one of the substituents on like one facing towards the front and another one facing like going backwards, how would you, I don't know if that makes sense, but how would you like?
Why don't we take a look at the stuff that's in the exam review? Because I think that can help us with that.
Okay.
Okay.
Sure.
So let me open the exam review and we can start sharing that screen and then we can start talking about that.
Okay.
Because I think the stuff that's in the exam review is going to be closely aligned with what we need. Let me find the exam review one more time.
I have another question, but it's more on the homework. There's like one particular part of the homework that I'm not familiar with. It's the question, it's the multiple choice question where which of the following products that will not give you 1-methylcyclohexene, and there are 4 possible choices.
So you want to talk about homework questions?
Yeah,
there's only that first one. I got that first one only.
Okay, well, let me open the homework questions and then
yeah, that's what I was trying to explain, what Devin was saying.
Okay, so just give me a second so I can find your homework question. Does anybody remember what question number that was?
It was the first one of homeworks, of the
14?
latest homework.
On homework 14?
Yes, the very first one.
Oh, okay, I love this question. So let me share my screen with you so we all can be looking at the same thing. Okay, is this the question that you're thinking of?
Yes.
Okay, which alkyl halide cannot lead to this product in an E2 reaction? Okay, so let's apply the things that we just learned and that we just talked about. Your E2 elimination is going to happen between the carbon that has the leaving group and one carbon that is directly adjacent to it, right?
Yes.
That's what we just discussed. So let's look at compound A. Here is, you see my cursor, right, Devin?
Yes.
Here is the carbon that has the leaving group. The leaving group is the chlorine. And I'm supposed to make a double bond right here in this position. Is this carbon in the right position for me to make a double bond right here?
Yes,
Yes, it is.
it's
So
possible.
A can allow me to make this product. Everybody okay with A?
Yes.
Okay, let's look at B. I'm supposed to make a double bond that ends up right next to this methyl group, right?
Yeah.
Okay, so here's the carbon that has the leaving group, that's the chlorine.
Mm-hmm.
Can I make a double bond right here?
Yes.
Yes. Would that lead me to this?
Yeah, it's possible.
Yes, it is possible, right? Because I'm making the double bond right next to a methyl group. Now, let's look at C over here. C is looking a little suspicious because look where the leaving group is, okay?
Yeah, it's attached to that carbon.
It's attached to this carbon. So if I make a double bond by eliminating this chlorine, where's the double bond gonna form?
Well, it's gonna form near the carbon. It's not gonna be forming near the.
It's gonna form right out here, right?
Yeah, it's not gonna
Is that
form.
what you want?
No, we're looking for what it can't be.
It will
So
not,
it will never.
be able to form this product, right?
Yeah.
So the correct answer would be C.
Mm-hmm.
And let's look at B, just because we're here, right? Here's the chlorine, here's the carbon that the chlorine is attached to. If this chlorine leaves, could I make a double bond right here?
Yeah.
Yeah, and would that lead me to this?
Yes.
Yes. So the only one that doesn't work is C, and the reason why it doesn't work is because the
It's
chlorine
attached to
is in
that
this
carbon.
carbon, and I have to make a double bond.
You have to make a double bond near the carbon. You can't be near the.
You can make it between the carbon that has the leaving group and a directly adjacent carbon.
Mm-hmm.
Got that?
Yeah, but you can't. Yeah.
So the only one that doesn't work is this guy for that reason.
Okay.
Okay? Kara, did that make sense to you?
Yeah, and I just saw where a guy named Jason said, but for D, is it not anti? Because that's what I thought as well.
I think
So here's what you need to worry about, Kira. You're going to eliminate this chlorine, and you're going to eliminate it with a carbon that is directly adjacent to it. Is this fixation with anti helping you to get to that product? It's not helping you, right?
Oh,
Can you let go of it right now?
no. Yes.
Okay, let go of it. All you need to know, I cannot talk to you right now, I'm sorry, I'm teaching a class. All you need to know is you're gonna make a double bond between the carbon that has this chlorine, which is this guy, and a directly adjacent carbon. Can you make a double bond right here?
Oh,
Yes, you can.
yes.
And is that product gonna be the same that you have up here?
Yeah. Okay.
Yes, it is. So can you let go of this anti-nonsense right this minute?
Yes.
Yes, stop worrying about if things are anti or not. What you need to worry about with the E2 reaction is where is the leaving group? Because you're gonna make a double bond on a carbon that has to be touching the carbon that has the leaving group.
Okay, I see.
Got
Why
that?
wouldn't- Sorry.
Yeah.
Why wouldn't we like choose from the other side with just 2 hydrogen attached to the carbon?
I'm sorry, what example are you looking at, Zia?
For D, why wouldn't we go the other way and choose the carbon that has just 2 hydrogen?
You're gonna make 2 products from this reaction. You can make one here and you can make one here. Now, you're asking me, why don't we choose this carbon that has 2 hydrogens attached to it? How many hydrogens are directly attached to this carbon up here?
1.
One.
Just one. Wouldn't that be better?
Oh,
Would
right.
one be better than 2?
Right, yeah.
So you will make 2 products from down here, but the major product that you will make would be this guy.
And the question's asking which one of these will never allow you to make the product that's shown above.
Exactly. So the
Not
correct
every
answer-
possible one, just you can't make it.
The correct answer has to be C because you cannot make a double bond in a carbon that is away from the leaving group. Make sense?
That makes sense.
Okay. Any other homework questions, or can we move on to the exam review? Because I'm worried we're going to run out of time.
Yeah, well, we can move on to the exam
How come
review.
the cat said for A, will double bond be in 3 positions, or will it only form in the ring?
Mason, I can't help. Here, you say that louder?
Can you hear me now?
Yes.
Okay, someone said for A, can the double bond be in 3 positions, or will it only form in the ring?
And for A, the double bond can be formed here, or it can be formed here, or it can be formed on the outside of the ring. Any of the carbons that are touching this carbon can make a double bond.
Cool.
Which one of those would be better? The ones in the ring in which the carbons have 2 hydrogens, or the one outside the ring where the carbon has 3 hydrogens?
In the
In the ring.
In the ring, because they have 2 hydrogens, right? So for E2, guys, apply Zaitsev's rule, okay? Apply Zaitsev's rule. Look at the hydrogens in the neighboring carbons. The one that has the lowest number of hydrogens, that's the one you want to go for. Got that?
Yeah.
Okay. Last call for homework questions. Are we good with the other homework questions? I don't hear anybody saying no, so I'm going to stop it with the homework. Okay. And it seems that the 1 propene question has been answered. There's no such thing as 1 propene. It's only propene, okay? If you have 3 carbons and you make a double bond between the first and the second one, it'll be the same as making it on the other side. So that compound is called propene. Okay, now for real, let's talk about this exam review. Because I'm getting nervous that we're not gonna get to it. Why won't this let me show you my exam review? Hold on one second. Seems that I have to close some windows so that I can get to the right one to share with you guys. Sorry about that, guys. Sometimes it's really hard to figure out what Zoom will let me share and what it won't let me share. Okay, let's see now. There we go. Okay, so exam review. Remember, please, that all the answers to the exam review are down here at the very end, okay? So it's not like I'm throwing you in the deep end without a paddle. You know where to find stuff. Okay, for question number 1, which compounds contain stereocenters? What should be our strategy for answering this question? What should we do?
Draw it.
compound.
Draw them, right? Draw those compounds, because you can't find stereocenters just by looking at somebody's name. That's very important, okay? Draw all 4 of them, and then look for carbons that have 4 different substituents, 4 uniquely different substituents, okay? Did anybody have trouble with number 1, or is that more or less coming along? Okay, didn't hear any trouble, so I'm gonna move on to the next one. Number 2 asks you to arrange the substrates in order of increasing SN2 reactivity with sodium cyanide. Bromoethane, 1-chloro-3,3-dimethylpentane, blah, blah, blah. How do we go about answering this question?
Well, there's a reactivity order about which one increases or decreases SN2 reactivity.
That's true, Devin. So would you agree with me that it might be a good idea to draw these things first?
Yeah.
Not try to do it just by looking at the name, right?
Yeah, because some of them you can't just, especially some of the more complex
if they're
ones. You
primary,
can't.
secondary, or tertiary just by looking at their name, right?
Yeah.
So draw each one of them and then use the order of reactivity. What would be a better substrate for SN2? Primary, secondary, or tertiary carbons?
Primary.
Mary.
For SN2, the best substrate would be primary, right?
Mm-hmm.
Then secondary, then tertiary.
Yes.
So if you were going to arrange those substrates in order, the answer is not provided to you. That's not very helpful. Okay, so let's do it so that it can be helpful. Did you guys get a chance to draw these substrates?
Yes.
Yes. And what was any of them a primary substrate?
Yes.
Yes.
There's one.
Bromoethane was a primary substrate. Was there any other one of them that were primary?
No. Doesn't look like it.
Okay, so I think we're gonna need the whiteboard if we're gonna answer this question. Let me make sure that I have the question with me so that I can put it on the whiteboard for you. Okay, so let's go over here. Let's go to the whiteboard. And let's clear this up. And now we're gonna draw this, guys. So the first one is bromoethane, right? So bromoethane would be CH3, CH2, capital H, Br. So that one is what we would call a primary substrate, right? Here's your bromine attached to a carbon that has one carbon neighbor. The next one on the list is 1-chloro-3,3-dimethylpentane. So 5 carbons on carbon 1, which is right here. We have a chlorine attached to it. And then 3,3-dimethyl, 1, 2, 3, means that right here, coming out of this carbon, we should have 2 methyl groups. We got that one? Yeah?
Yeah.
The next one here is 1-chloro-2,2-dimethylpentane. And here is the chlorine. Again, forgive my drawings. They're not very cute, but they will get the job done. And then the next one was 2-bromo-2-methylpentane. So let's draw that one. And here is a bromine. Okay, so is that, did I get all of them? 1, 2, 3, and 4. Yes. So we have 4 of them. Let's look at the first guy over here. What kind of carbon is this guy? Primary, secondary, or tertiary carbon? Anybody? What kind of carbon is this guy right here?
Primary.
That is a primary carbon.
That's a
right?
problem.
So we're gonna say that carbon is primary. How about the carbon down here? Primary, secondary, or tertiary?
Primary.
Primary again.
Also primary, right? We had said that this carbon right here, this one, was also a primary carbon. So it looks like we have a whole bunch of primary carbons. And what do we have in our hands here? What kind of carbon is this guy?
Tertiary.
Tertiary, because it has
That's
3
tertiary.
carbon neighbors, right? So that would be a tertiary carbon. So if we have to put them in increasing order of reactivity, which one of these guys would be the lowest one, the least reactive?
Tertiary.
This guy, right?
Tertiary.
So this should be the least reactive. You guys agree with me?
Yeah.
I hope so. So that's going to be the least reactive one. The other 3 are all primary carbons, and we're going to have to make a decision about those primary carbons. The first thing that we can use to make our decision is the leaving group. If somebody has a better leaving group, we need to consider that to be a better substrate. What is a better leaving group, bromine or chlorine?
Bromine.
Bromine is a better.
Bromine is a better living group.
So would you agree with me that this guy up here has to be the most reactive?
Yes.
And now our job is to discriminate between the 2 guys that are in the middle, right? They're both
Yes.
primary carbons. They both have chlorine as the leaving group, so they're very similar. So the question becomes, which one of these guys is easier to attack from the back? Because this is an SN2 reaction, okay? So if you have big bulky neighbors on the back of the molecule, that's gonna affect your outcome. The closer the big bulky neighbors are, the worse it is. You guys might remember that this is a methyl group here, right? And this is another methyl group here. And so are these 2 guys up here are also methyl groups. Between this compound here, which I'm gonna call A, and this compound here, which I'm gonna call B, which one do you think is easier to get to the active side from the back? A, where the methyl groups are far away, or B, where the methyl groups are right there next to the active side?
A.
A is gonna be better, right? So if we're doing order of reactivity from least to most, let's say that our least reactive, we're gonna call that guy least reactive. We're gonna call that guy, should we do it? It says to do it in increasing order of reactivity. So least reactive is gonna be 1. Most reactive, right here, is gonna be 4, okay? If this is least reactive and this is most reactive, what number do we need to give to compound A?
3.
No.
Compound A is gonna be number 3, and compound B is gonna be number 2. Got that? So this would be 1 least reactive, 2 second least reactive because of the big bulky neighbors right next to it, 3 a little bit more reactive because the bulky neighbors are far away, and number 4 most reactive because it is primary, no big bulky neighbors, and an excellent living group. Did we get that? Yeah. Okay, and I will make sure that I reflect that on the key because that was not included on that key. Okay, so let's go back to the review and share that here. Okay, how did you guys do with the lactic acid? Were you guys able to build models to figure out which forms are R forms?
Yeah, I just drew them.
Say that again?
I was able to just draw them and figure it out.
Okay, I don't like that idea. I like much better making a model, but I respect your choices. Now, let's rank the substituents just to make sure that we're all on the same page, okay? Of the substituents that you have in lactic acid, you have a methyl group, you have an OH, you have this carboxylic acid, and we have this hydrogen. Which one of those has the highest ranking?
The alcohol.
The alcohol has the highest ranking because it starts with oxygen, right? And the rule says, the easy rules say, highest ranking is highest molecular weight at the first point of difference. So this is gonna be your blue substituent, which is the highest rank. Who is the second highest rank?
The carboxylic acid.
The carboxylic acid is gonna be the second highest rank. And who's gonna be the third highest rank?
The methyl.
The methyl group.
The methyl group, okay? So once you build your models, you should be able to figure out, according to the answer key, which is down here, that A was the correct answer to number 3. So 1 and 2 are the ones that are R forms, okay? Build your model to verify that there's no shortcut for building a model.
Dr. Williams,
Yes.
do you have any suggestions for students who don't have toothpicks or gummies or marshmallows to build their own model?
You don't have toothpicks and you don't have marshmallows, okay? Do you have any straws?
No.
No straws.
What about noodles?
Noodles would work great.
Okay.
Do you have noodles?
Yeah, like spaghetti.
Yeah, spaghetti noodles would work great. There's also, some people are able to, so straws work, spaghetti works. You could use like bigger noodles and make like a little fat model, you know, like using thick noodles to make the bonds. Let me think about that.
There are some websites where you can look up the compound and it'll show you like a 3D representation of it. So if you just like Google it, like PubChem, I think has 3D representations of all these different types of chemicals.
So Ben, Ben is suggesting that there are some websites where you can look up the compound and it will give you a 3D representation and it will let you rotate them around. The problem that I see with that is during the exam, you're going to have 20 questions, right? You're going to have a limited amount of time, and we're going to be struggling with trying to rotate this compound in the 3D space in the program. Wouldn't it be faster to just have a little model with the colors ready to go and use that reproducibly every time? Kayla, if you want to build a model out of spaghetti and you want to talk about it, we can do a Zoom after this this afternoon, and we can test your spaghetti model to make sure that it works. Okay?
Okay, sounds good.
And the same offer goes for anybody else who wants to test their model. I don't care how exotic your model is. I'm willing to try it with you. I'm available all afternoon and I'm available all day tomorrow. So don't let that hold you back, okay? Anybody that struggled with question 3, please let me know and we'll do a Zoom together and we will make a model work for what you have in your house. I promise you that we can do that. Okay, number 4, which of these alcohols are secondary? What are we looking for here? We're looking for the carbon that the alcohol is attached to, and then we determine whether that carbon is primary, secondary, or tertiary, okay? So this guy that we have here, number 1, the OH is attached to this carbon. How many carbon neighbors does that carbon have?
3.
3, so that's a tertiary alcohol, right?
Yes.
Oh, I was about to say it had 2, but the methyl counts.
The methyl counts, yes. Let's not discriminate against methyl groups. Okay, here's your OH attached to this carbon. How many carbon neighbors does that carbon have?
3.
3, so that's a tertiary alcohol, okay? Now here's an interesting one. Everybody gets confused because there's a double bond. The OH is attached to this carbon. How many carbon neighbors does that carbon have?
2.
2. And if it has 2, that is a secondary alcohol, okay? And then the last guy over here is attached to this carbon. How many carbon neighbors does that carbon have?
2.
2. So that makes it a secondary alcohol. So 3 and 4 are both secondary, okay? Okay, in this one here, they want us to give a detailed mechanism for this reaction. I'm not going to put the mechanism on the exam, just to give you a little peace of mind, but we should know that this cyanide, if it's going to attack that bromine, the cyanide is going to come from the back, and it's going to attack this carbon right here. And in the same motion, we're going to get rid of that bromine, right? The 2 things are going to happen at the same time. And if the cyanide is going to come in and it's going to replace the bromine, you need to have the cyanide end up in the place where the bromine used to be. Now, one thing about this question that I want to make you guys pay attention to. Do you see all the stuff that's down here on this molecule? Does any of this have anything to do with the mechanism of the reaction? Is it going to interfere? Is it going to be a part of it? No, right? The action is going to happen right here where your leaving group is. So this is going to be true for SN1, SN2, and E2. The action is going to happen on the carbon that has the leaving group. If you can find that carbon and you can make things happen to it, you will do well on the test. Does that make sense? What are we looking for? The carbon that has what? Nicole, please help me. You're my
The leaving group. The leaving group.
The carbon that has the leaving group. That's what we're looking for. Okay?
Is this question SN2?
This question is SN2. Yes, Taylor. How do we know that it's SN2? We have a primary carbon, which is a good SN2 substrate, and we have cyanide, which is a good nucleophile that we can use for SN2. And we can see on the other side that what happened here was we replaced this bromine with this cyanide. So that was a substitution reaction, and because it is a primary substrate, it had to happen through the SN2 mechanism, okay? Okay, question number 6. Do we know how to do question 6? What do we use for this one? What do we have in our notes that might be helpful if we're trying to answer question number 6?
Of reactivity?
The arrow of reactivity. That's right. You guys remember the arrow of reactivity?
Yeah.
Okay. If you don't remember it, this would be a good time to look it up. There are different substituents on this benzene ring, and they're located at different places within the arrow of reactivity. I feel like the only way for me to answer this question properly is to show you the arrow of reactivity one more time. And let's find the arrow. I wish I didn't have so many windows open. My life would be easier. Okay, so the arrow of reactivity comes from chapter 5. And if you scroll through it, you will get to this beautiful arrow that tells you where all your substituents are located. And we're gonna be looking at it right now. Do you guys remember the arrow of reactivity? There it is. So there were some substituents on that particular question that, that you can find in the arrow of reactivity. One of them was an OH substituent, right? If you guys don't help me, I'm not gonna do anything. I'm just gonna cry here in the corner and I am not gonna talk to you anymore. Help.
Yes.
What kind of substituents are we looking for in the arrow of reactivity? One of them was a phenol, is that right? Is there an OH group?
Yes.
Yes.
Another one was a CH3, an alkyl group.
Yep.
Yay.
What else did we have?
Cl group.
Was it a chlorine?
Yes.
Yes.
Here's chlorine right here. And the last one, did it look like this? Was it a ketone?
Yeah, there was a ketone.
There was a ketone. Okay. So we put them in the order in which we see them in the arrow of reactivity. Of those four things that we just named, the ketone would have to be the slowest one, right? Then the chlorine, then the methyl, then the OH group. Okay? So let's go back. After we looked at the arrow, let's go back and take a look at the review. Here we go. So of these guys, who's gonna be the slowest one? Because it says lowest first. According to what we just saw in the arrow of reactivity, which one of these guys is the slowest one?
4.
4 is the slowest one. So we're looking at answer B, which is looking promising. Was number 2 the second slowest one?
Yes.
Yes. And then number 1?
No.
And 3.
Yes.
Wait, it was? Oh, okay.
It was. And
Three.
then number 3. So the correct answer to this one was B. Slowest, then this guy, then this guy, and then this guy. Okay? Make sure that you have your arrow of reactivity ready to go so that in your worksheets so that you can use it for the exam. Okay? I saw a question on the chat about whether the exam was open notes or just the worksheets. I would expect you to use only the worksheets when taking the exam. All the information that you need is in those worksheets. And if we solve the problems with the model set so you can be successful with chapter 6, we should be able, all of you should be able to ace this exam with your worksheets and your model set, okay? That's my expectation for you. Obviously, I can't be in your house looking over your shoulder, telling you what the right thing to do is, but I want you to remember that I put a lot of time into teaching this stuff to you guys, and I'm asking you to now put the work back in getting the exam back to me, okay? So I trust you, and I trust that you have learned enough that you could do these things. So that's where we are with the exam. I'll follow up with an email with details about the exam, okay? I'm trying to make it as user-friendly as possible for you guys. Okay, question number 7.
You're the best instructor I've ever had at state, so I appreciate it.
Oh, well, thank you. That is so sweet of you. I really do appreciate that. I'm probably the most stressed instructor you have right now because I want this exam to be as good as it can be and you guys to be as successful as you can be. So let's look at question number 7. Starting with benzene, how could you prepare benzene sulfonic acid? Where can I find the answer to this question in my worksheets?
Sulfonation.
Common names.
Arrow of reactivity.
Well, they're only asking you how to prepare benzene sulfonic acid, so we don't really need the arrow of reactivity. But what we really need here is the reactions that came from chapter 5, right? So let's look at those reactions and see if there's one that allows me to make benzene sulfonic acid, which is this guy over here. You guys remember a reaction that lets you do that?
The sulfonation reaction?
Sulfonation. Can you see my screen right now? I'm sharing my overheads with you.
Yes.
That's the reaction that you need, right? Sulfonation reaction. What do we add to benzene to make the sulfonation reaction go?
Sulfuric acid.
Sulfuric acid and heat, okay? If you have sulfuric acid and heat, you can do a sulfonation reaction. So that's where we are with that one. Okay, back to the review. I don't know why, but my computer is being very strange and it keeps trying to get me out of the review window and doesn't want to show it to you. And I don't know why that's happening. Okay, let me close the overheads and see if I can make this work. Sorry, guys. Technical difficulties. Okay. Let's close that and that. And let's see if now we can show the exam review. It just won't let me do it. And I have no idea why, because it's right here. Here we go. Finally, we got it. Okay, so going on to question number 8. Any ideas on how we could solve question number 8?
Do the reactions.
We're gonna need our reactions from chapter 5, which are in the worksheet, and we're gonna need the arrow of reactivity, right? So we're gonna do 2 reactions in a row. The first reaction here, I don't know if you recognize those conditions, that is a nitration reaction, okay? So you would do a nitration reaction, which is gonna allow you to make nitrobenzene, and then we would use the arrow of reactivity to figure out how to do the second part, where to add the chlorine. So let me go to the whiteboard here for a second so we can do that reaction. And let's clear that. So we're gonna start with benzene over here. That is a sad looking benzene ring, but you get the idea. If you ever show these drawings to anybody, I will pretend that I didn't do them, just so you know, okay? So don't be blackmailing me with my poor drawing capabilities. Okay, the first part of the question says we're gonna add HNO3 and H2SO4, right? And now we're gonna have an arrow here. Okay, so what do you expect from that first reaction? What will I make as a result of that first reaction?
Nitrobenzene.
Nitrobenzene, right? So here's my benzene ring, poor thing, looks really, really sad. And here is my nitro group. Got that? And now there's gonna be another reaction that is gonna be done on nitrobenzene. And I think it says that we're gonna add Cl2 plus FeCl3. What are these conditions for? What would I add if I put chlorine and iron trichloride in that mixture? What am I trying to add to the benzene ring?
Cl.
A Cl atom, right? Can I add it just anywhere, or is there a specific place where I should be adding it?
Meta.
There's a very specific place, and that very specific place is meta, right? Why is it meta? Because this guy up here is what we call a meta director. And you can find that information in the arrow of reactivity. Since the nitro group is a meta director, the chlorine can only attach to meta. Is it clear to you guys that either one of these meta is just as good as the other one? They're equivalent positions. You see that?
Yes.
Okay, so let's draw the product. The product, you should have a little arrow here. Here's the arrow, and then the product's gonna look like this. You're gonna have a nitro group. I know that's a terrible benzene ring. You don't even have to look at me. You're gonna have a nitro group, and then in the para position, I'm sorry, in the meta position, you're gonna have a chlorine that has been added to it, okay? So what would be the name of this compound that we have here? Help me write down the name.
1-chloro-3-nitrobenzene.
Or we could use ortho-meta pair nomenclature, right? Which would simplify our lives a little bit. So that would be meta
Chloro
nitrobenzene.
benzene.
And if we want to use numbers, that would be 1 chloro, 3 nitrobenzene.
And so, Dr. Williams, I was wondering, I know you want to encourage us to use the meta, but what happens like on the test if we just happen to forget and we do write 1 chloro, 3 nitrobenzene? Would that be okay?
Then what I'm going to do is if I want you to use ortho-meta nomenclature, I will tell you.
Okay.
Or I will give you a multiple choice question like the one that we have on the review right now. Okay?
Okay.
So I'm trying to write the exam, Kiara, so that we don't have any misunderstandings and you don't have to be wondering what's on my mind.
Okay.
Another thing that you should know is, and by the way, 8 was answer B, as you can see here, okay? So if I give you a question like this on the exam, you can just choose the best alternative. The other thing that you should know is while you guys are taking your exam, I'm gonna be on Zoom waiting for your questions. So if you're taking the test and you are not sure what I mean by something and you're taking it during the class time, you can come and ask me questions, okay?
Okay.
So we have that alternative available. Okay, number 9 is what we call an acylation reaction. Does everybody recognize the acylation reaction here? We're trying to attach this piece that starts with the carbonyl, we're trying to attach it to our benzene ring. And in this case, we had to combine the area of reactivity and the acylation reaction. So I'm gonna let you guys take a look at the product of that one, and that one should be fairly straightforward. Number 9 and number 10 combine reactions from chapter 5 with the area of reactivity. So make sure that you guys know how to do those, okay? Number 11, they're asking you to rank the substituents in order of decreasing priority according to the EC system. Why am I bringing back the EC system one more time? Because it is the same system that we use when we're ranking things for R and S, okay? So that's why. So of all the things that we have here, which one do you think should be the highest rank one according to the EC system?
4.
And Nicole, you're saying 4 because it starts with an oxygen, right? Which has the highest molecular weight.
Mm-hmm.
This guy, number 1, also starts with an oxygen. But between 1 and 4, I assume that you're saying that 4 has a higher ranking because there are more carbons attached to that oxygen. Is that correct?
Correct.
So 4 is the highest rank. And what comes after 4?
1.
1. And then between the 2 guys that have carbon attached to them, which one should
2.
have the highest rank?
It should be 2.
It should be 2 and then 3. So the correct ranking should be, we start with 4, then we go to 1, then we go to 2, and then we go to 3, which is
For 2, is it bigger because it has carbon than oxygen, which is higher than hydrogen?
Yes, ma'am. That's exactly
Okay, just to
right.
make sure.
This
Okay.
first part is identical, right? Carbon to oxygen, carbon to oxygen. But then when you look at what else is attached, this one has a higher molecular weight substituent. Got that?
Yep.
Okay. This is a freebie. Arrange these living groups in order of increasing living group ability. Which one is the best living group from that list?
2.
2, which is iodine, right? Big, bulky, not very electronegative. After 2, which one is the next best living group after iodine?
Bromine.
Bromine is the next best living group. Not as big, but still big. Not as electronegative, but still electronegative. And then between fluorine and chlorine, who is a better living group?
Chlorine.
Fluorine.
Chlorine. And then who is the worst living group in the whole wide world?
Fluorine.
Fluorine. Okay, fluorine does not leave. Fluorine, if you make a bond with fluorine, if you make a bond between carbon and fluorine, that bond is literally impossible to break. Okay, well, nearly. Not under the conditions that we know. So don't expect that bond to break. Okay, Devin, are you still around? Because I wanted to point out to you question number 14, which is very similar to what we just did in the homework, but with a different formulation. I think Devin has left, but we can still talk about it, the rest of you. Does question 14 look similar to the first question on the homework?
Yeah.
But backwards, right? They're asking you, which one of these guys will allow you to make a double bond here on the outside? See that? Can I make a double bond here on the outside? Can I make this double bond if I start with some of the other things that I have named here? Which one would be the best alkyl halide to make this double bond?
C.
C, right? Because here's the carbon that is attached to the chlorine. And if I take away this chlorine and I make a double bond, I can only make that double bond right here. See that?
Yeah, that makes sense.
So C is the best answer to this question, okay? Is there another possible alkyl halide that is hiding here that could make that double bond in a hurry if we had to?
A.
A could make that double bond, but it wouldn't be our first product. It wouldn't be our major product, right?
Correct.
It wouldn't be our major product because we have better carbons down here. So we would rather make the double bond here or here. Does that make sense?
Yes.
Okay. So I jumped question 13 because I got so excited about 14, but we have time for 13. What are optimum conditions for an SN2 reaction? So what do we know about the SN2 reaction? What is the best substrate for SN2?
Primary.
Primary, right? So of the carbons that we have listed here, is this guy a primary carbon?
Yeah.
How many carbon neighbors does this carbon have?
1.
One.
It only has the one. This is the only carbon neighbor, so that is primary. Number 2, excuse me.
It's
Is it a
2.
primary carbon?
No.
Secondary.
Secondary. Number 3, is that primary?
No.
No.
What kind is that?
It's
Secondary.
tertiary.
Oh, tertiary. Yeah.
Tertiary, that's right. And the last one here, what is that primary, secondary,
Yeah.
or tertiary?
Primary.
Primary. So of the things that are listed here, there's only 2 of them that are primary. Those would be the ones that I would consider first because they're asking me for optimum conditions. You agree with me?
Yes.
Yeah.
So I would have to consider number 1 or number 4, okay? Now, the solvents for number 1 and number 4 are the 2 solvents that we have named as useful solvents for SN2. So you could have acetone, you could have the MSO. The solvents are equally good, okay? So no advantage there. Both are good SN2 solvents. The nucleophiles are both good. I know you're not very familiar with NaSH, but I will tell you NaSH is very similar to NaOH, okay? So this is a good nucleophile for SN2. This is a good nucleophile for SN2. What is left between 1 and 4 that may make me decide that one of them is the best one?
The leaving group.
The leaving group. And which one is a better leaving group, chlorine or bromine?
Bromine.
Bromine. So of this list, what is the absolute best conditions for SN2?
4.
Number 4. And then also pretty good conditions for SN2?
1.
Number 1. Okay? Can you see why we discarded number 2 and number 3? What was wrong with number 3?
It was a tertiary.
It was a tertiary substrate. And what was wrong with number 2? We had a secondary substrate, which is not the best for SN2, but there was something else going on. Is this a nucleophile that we can use for SN2?
No.
No, we said nucleophiles for SN2 always come in the form of salts, right? Sodium chloride, sodium bromide, sodium iodine. Is this guy salt? No, that's methanol. And is this a good solvent for SN2, water?
No.
No, the solvents for SN2 have to be aprotic. So acetone or DMSO. That's the reason why 1 and 4 were the best choices for this question. We all got that? Yeah? Okay.
Yeah.
The answers are down there for you to take a look at. It's exactly 1 o'clock. Does anybody have any pressing questions that we should address, or is anything on the chat?
I think there was a question in the chat.
Okay, let's see. Would you be able to give an example of this bullet from the study guide? Give a set of conditions, predict the outcome of a reaction in which elimination and substitution mechanisms are in competition. Okay, look, I'll give you the only example. I'll give you 2 things. First of all, I didn't put that on the test, okay? So maybe stop worrying about it. Thing number 2 that could be useful. The only time in this class where elimination and substitution mechanisms might be in competition is when you have a nucleophile like sodium hydroxide, okay? Sodium hydroxide is a tricky nucleophile because it's also a base. So sometimes it will do elimination, sometimes it will do substitution. So what I'm doing is, Taylor, I'll get to that question in just a second. So what I'm doing on the exam is, if I want you to do an elimination reaction, I'm giving you a big, strong base, like sodium methoxide or sodium ethoxide, like the ones that we saw today on E2, okay? If you see those big bulky bases, I want you to do E2. The other thing that I'm doing is I'm trying to make it very clear on what the expectation for the reaction is, so that I don't think you're going to be forced to decide, is this going to be elimination versus substitution? I don't feel like we practiced that enough, so I didn't put that on the exam. Does that answer your question, Luke? Okay. And then Taylor has a question. What is the relevance for activators and deactivators in the area of reactivity? So that's a very good question. If you go back to the area of reactivity, Taylor, you will see in that video that I covered that in 2 separate slides. In one of the slides, I talked about orthopara directors and meta directors, which I think you feel pretty comfortable with, right? And on the other one, I talked about activators and deactivators. The way to ask a question where you have activators and deactivators is to ask you which one of this reaction would go faster or which one would go slower, okay? So in the review guide that we just did, we use the area of reactivity and we look for activators and deactivators. Remember that? In that question where we were looking for OH and methyl and the ketone and the chlorine, that's exactly how you use that arrow in terms of activation versus deactivation. An activated reaction goes faster, a deactivated reaction goes slower. Does that answer your question?
Yes, thank you.
Okay. Anybody else has any questions left before we stop the recording? Are we good? Do you guys feel more or less prepared for the exam?
Yes.
Yes.
A little better now?
Yeah.
Okay, so reminders. Fill your worksheets, okay? Make sure that the worksheets are working for you. Make sure that you have Stacev's rule on the worksheets. Stacev's rule is the one for the elimination reaction, the one that tells you where the double bond goes, okay? Make sure that you have your area of reactivity. Don't photocopy the area of reactivity. Don't use the one from the book. Use your own that you made with your own hands, okay? It's really important when it comes time to find things in the area of reactivity. And if you are still not comfortable using your little model set for chapter 6, send me an email and we will do as many Zoom meetings as needed until everybody feels comfortable doing that, okay? We will be crafty and we will make a model set for each one of you if needed. I think that based on the chat, there doesn't seem to be any more last minute questions. I will send an email today reminding you of when we're taking the test, which is during class time tomorrow, but you will have extended time. You will have 3 hours. If you have disability accommodations, I will give you extra time based on your disability letter. And if anybody needs to take the exam at a different time, you need to let me know today so I can make those arrangements, okay? Got that? Okay, so I'm gonna stop the recording because I think we're all more or less in agreement.